So it's important to talk about discontiguous address spaces because this happens quite often in computing. This is chapter 11.8. So a contiguous address space is where all locations correspond to physical memory. This is pretty inflexible because it requires all the sockets to be populated. What's more popular is to have basically one or more blocks of the address space that aren't corresponding to physical memory. Therefore, we can have certain areas of the virtual memories correspond directly to address spaces in physical space, and others would correspond to nothing, which we would call a hole. So only part of the memory is represented in that situation. So if it is contiguous, every address corresponds to an actual underlying physical memory location. Otherwise, there would be one or more holes, and this would be called discontiguous. So if a processor attempts to read or write any address that does not correspond to physical memory, an error would happen, and therefore we would be careful about doing such a thing as programmers. This also allows us to decide how much memory would actually be installed at runtime. So it's important when we're talking about discontiguous address spaces that we think about the fact that a virtual address might appear in the virtual space to be mapped to two physical memories, and part of each physical memory could be actually omitted. And if this happens, we have a situation in which there actually could be holes that exist. If we take a look, for example, at the illustration given, we see that n divided by 2 minus 1 would be the case where a hole is present. N divided by 2 actually would be a memory 2 that exists. This is going to two physical memories. So it's not contiguous because only part of that memory is represented. So if some of the memory gets omitted, part of the virtual address space becomes unusable. The virtual address space is basically defined when it's created, and this way we can basically plug and unplug memory chips easily and just decide what the virtual address space is at that time, and it's going to correspond to whatever the underlying memory is. So the goal is to allow multiple applications to run concurrently. This is sort of why we do virtual memory in the first place. The examples that we showed before can show that memory systems can present a processor with virtual address space that differs, but basically what we want to look at now for the rest of the chapter is more complex schemes that allow us to allow multiple applications to run concurrently and to prevent other applications from interfering with each other. The trick is actually to provide separate virtual address spaces for each program. So for example, here's 4 virtual address spaces that are mapped to a single physical address space. These are partitions, and basically what will happen is to allow for multi-programming, we will have each virtual memory to establish a separate virtual address space for each program. So this is actually what we call partitions. These were popular in the 60s and 70s, but have since been replaced, and we'll talk about why and how. Basically, this was saying that each program would run on a certain partition of memory. This became quite cumbersome. It required for you to understand that what is the underlying physical memory and what's your program going to actually run on. Instead, we ended up creating our virtual spaces dynamically. So we had the processor configure the MMU. So the address space ends up getting mapped and changed at any time. So access to MMU has to be restricted to the operating system, and the operating system runs in real mode and it has access to physical addresses, but it presents its memory in a virtual memory scheme to the programs that are running on top of it. So a couple technologies exist for this kind of dynamic space manipulation: base-bound registers, segmentation, and demand paging, and we'll take a look at each one of these in turn. The idea of base-bound registers is to use a mechanism that basically provides a single virtual address space and maps that space onto a region of physical memory. So the name is actually referring to a pair of registers. There's a base register specifying the starting address and a bound register specifying the size of the address space. So that's a very easy way to dynamically sort of allow for whatever is on the physical side and store it in a register, and two registers in this case, and allow the operating system to know where that exists. So here's an example using base-bound registers. So the base register specifies the location of the virtual space. Bound register specifies the size. So this virtual space is defined from 0 through m, which is a subset of 0 through n. So we use those two values to specify how the virtual address space maps onto the physical address space. It's powerful because an operating system can change the mapping dynamically. It can dynamically change where that virtual space is decided to be. So this virtual space is here for this moment, which might be for a certain program that's running, but then maybe the next time it runs it's going to actually be in a separate space. So in practice what happens is multiple applications will be allocated a separate area of physical memory, and the OS will set base-bound registers before the application runs. So it's going to set those registers before the application runs, basically by finding out what amount of memory it's required to have, setting those registers, and therefore checking each memory reference as it comes in to make sure that it's part of those, that it's inside of those bounds. Any reference outside of the valid range would result in an error. Of course, this is hard to do as a programmer, although you can do it in C and C++ because the C and C++ allow you to do references outside of the bounds of the virtual memory space. If you do so, you will get an error. So the concept here is that it's going to support multi-programming, it's going to provide protection, and we're going to allow for reading or altering memory that has been allocated to another program. That's what we call the concept of protection. Another thing that's used is segmentation. So the mappings we described earlier are intended to map to complete address space. But in reality, a lot of segmentation occurs. So to reduce the amount of memory needed, basically architects have proposed that each program is divided into variable size blocks, and only the blocks of the program that are needed at any time can be loaded into memory. So we chunk up the program into blocks, and we load those blocks only as needed. And the operating system is configuring the MMU to establish the mapping between those virtual addresses and the pieces that are actually used. So this is known as segmentation, and it allows for fine-grained mapping between basically parts of the program that are running the virtual space and the actual physical space. So the segments is only placed in physical memory as it's needed, as the program is running. Otherwise, if the segment is no longer needed, the OS moves it to disk. The problem with this is that we need hardware to support moving segments efficient. We can use variable size segments, but this does cause memory fragmentation, and the fixed size elements can be too small or too large. In reality, this means that it's seldom used. It's a scheme that basically allows the programs to be divided into variable size blocks, but because of the fact that they are variable, it means that heavy segmentation exists and it needs to fragment, or it needs to defragment very often. So what's used more often is demand paging. This is an alternative. This is the most popular virtual memory technology. Demand paging allows for pages to be loaded in and for use of page replacement algorithms. So it's going to divide programs into fixed size pieces called pages. We're not attempting to align page boundary with procedure here. We're just simply dividing it into absolutely fixed size pages, and then those pages are going to be loaded into physical memory. Average page sizes can be about 4K bytes. So 4 kilobytes. We do need some special hardware that handles address mapping and detects missing pages, and we need the software to move between external store and physical memory. So in other words, the hardware is going to provide a paging system to handle every demand aspect of this system, whereas the software is going to provide a way of managing the memory. It has to decide which page or pages to keep in memory and which to keep on external storage. The paging hardware is part of the MMU. It intercepts the memory references, and if the reference page is present in memory, it translates this. If it's not, it's going to generate a page fault, and it's going to allow the operating system to handle that page fault. But what needs to happen on a page fault case is it has to load it into the paging system. It's going to inform the operating system that a fault occurs, and it's going to let the software handle that. It's going to identify, the software then is going to identify the page that is needed, locate it on secondary storage, move it into memory. So it's going to record the location of, the software is going to record the location of all the pages. It's going to fetch pages on demand. It's going to configure the MMU. It's going to do quite a bit of work. That's why operating systems are so important, because they have to actually do the hard work of maintaining the overall memory management. They have to figure out the page replacement algorithms, and they have to be able to fetch pages on demand from hard disk. Initially, page replacement is going to basically, applications are going to reference pages, and any reference page is placed into physical memory. Eventually that memory becomes full, and existing pages have to be written to disk before memory can be used for a new page. So as we fill up our physical memory, we eventually have to replace pages that have already been used, and that's what we think of as page replacement. So the idea is you're filling up kind of like a buffer, if you will, or the physical memory itself, and as you load more and more of the program that's being run into that memory, eventually you have to loop around and start deleting things that haven't been used very recently. The actual details of the algorithms are beyond scope of this class, but there are advanced topics in page replacement algorithms that exist both on the hard machine architecture and organization level, as well as the operating systems class. We'll discuss some of this. As far as paging terminology, remember that a page is a fixed size piece of a program's address space. A frame is that slot in memory that's exactly the size of a page. A resident is a page currently in memory, and a resident set is pages from an application that are present in memory. Those are just some terms that, just to kind of throw out there to let you memorize and define. So the data structure that we're going to use for this is called a page table. There's going to be one per application, and it's a one-dimensional array indexed by the page number. It's going to store the location of each page in the application, and that's going to be either in memory or on disk. And this way we can do a page table lookup to find out where that actual memory is. And if we have a null pointer in the page table entry, that means the page is not currently resident. If we take back a look at this, we say that null means a page is not currently in memory. This is what that would look like. A page table would basically have, as you can see, it's going to physical memory locations. Null pointers in the page table mean that that page is not currently resident, so that actual page is not loaded into physical memory at this current juncture. So for any virtual address V, we can find a physical address P. This means we can determine the number of pages on which V lies and use that page number as an index into the page table to find the location in memory. So we have to determine how far into the page V lies and convert that into position in frame memory. So the page number is computed by dividing the virtual address space by the number of bytes per page. which is k. So that number equals v over k. And then the offset, quite like the byte addressing stuff we saw before, is v modulo k. So it's just the offset into that space. So it's, if we're looking for, we can use N and O to translate the virtual address v into a physical address, which is basically a page table at N plus O, which is our offset. Again, we cannot afford division or remainder operations for memory references, so we use the powers of 2 strategy, and we let each number of bytes per page be 2 to the k. Offset O ends up being the lower order k bits, and then of course the higher order determines which page number it's actually on. And the computation ends up being page table at a certain location, in this case the higher order bits or lower order bits of v. So ORed meaning and together, or not OR, but add together the lower order bits of v plus the page table results of the higher bits of v, and that way you get your actual reference to physical memory. So here's an illustration. So basically here's our high order bits that are coming from the page table F, you see them, and our virtual address O. So N goes into the page table, is translated, gives us F, and then O is the offset, essentially. So presence, use, and modified bits are also present in most paging hardware. This allows us for page replacement schemes to basically say that certain pages have been used. Certain pages have been modified, for example. In that case, maybe we don't want to get rid of it. And that means that we have to store these extra bits. So it's kind of like dirty bits, like it's been modified, so therefore set some bits to say that's been modified. And these are replicated both on the hardware and software end. So as far as page table storage, page tables do occupy space. It's either going to be in the MMU or in main memory. The space that they occupy is basically going to be determined by how big that page table actually is, how many references it has, and how many bits are used to represent those references. So here's an example. This is one entry in a page table. So this is showing the I'm sorry, this is physical memory divide in architecture that's storing page tables in memory. So basically the operating system is stored in memory, the page tables are stored in memory, then the frame storage. At first I thought this was going to show us a picture of how it looked in memory, and actually that is way back here. So as you can see, F is the page table reference, and that's going to be divided up to however many bits it requires to do the page table reference. So paging has to be used in this case for instruction references and for data references. This can become a bottleneck, and so we have to optimize it. We optimize it with what we call a translation look-aside buffer. And translation look-aside buffers are going to basically maintain where it's a form of CAM basically, and it's going to store recently used values from a page table. So when it's first translated, MMU is going to place a copy of that into the TLB. And on successive lookups, it can look in the TLB first before it has to actually go through the hard work of searching through the page table. It's a hardware mechanism. It's a form of CAM, as I said, and if there is mapped into the TLB, then we don't need a page table reference, and we can just return the mapping immediately. In practice, we need a TLB no matter what. It's just not sufficient to do this without a TLB. So we can accommodate our paging systems. In other words, we can group related data items on the same page. We can reference arrays in order that access contiguous memory locations as well. So contiguous memory locations ends up basically being, so what we would like to do is do row major order. So one row, then another row, then row 2. And so our location of A comma I of, or A of I of comma J is given by the location plus I times Q plus J, where Q is the number of bytes per row. So it's usually the programming language and compiler that determine what, if it's row major order form or column major order form. But the programmer can control how the program actually iterates over that actual array, and that can greatly influence things. So for example, the first would be optimal, where we start with 1 to n, and we go from, which is basically the row major ordering, and we go from 1 to n, and then for j we go from 1 to m. Non-optimal would be to basically reverse that and have I going over the columns, or j going over the columns, and inside of it I going over the rows. It would be possible technically from a programmatic point of view, but since things are ordered like this in memory, with row 0, then row 1, then row 2, then row 3, that's row major, and that's how most things are organized. So usually you're going to want to do it in this optimal format. In fact, I've noticed personally some loop stuff was changed during performance optimizations for various games that I worked on in favor of this optimal structure of doing row major order. And of course here is kind of a simplified example, but things can get more complex as you get your iterations buried deep within code. So in summary, the virtual memory system is there to present an illusion to the processor, to basically hide details of how the word addressing is going to look, and basically allow us to effectively address everything. It's going to offer convenience for the programmers, support for multiprogramming, and protection so that we aren't currently using certain parts of physical memory by more than one program. Demand paging is the most popular, but we've also looked at basebound and segmentation. So that is it for your videos for Makeup Week. There is a quiz online which talks about some of this stuff. Be sure you read chapters 9, 10, and 11 before you take that quiz, which is what I've covered today. See you in class.